Hello. Today we'll be talking about the fun world of mod, or modular mayhem. And so first talk about how can we view mod as an equivalence relation with equivalence classes? How can we kind of think mod n and do things in the mod n world? What are modular inverses and how can we find them? And then also how to reduce things mod n via recursive squaring and Fermat's little theorem. So let's go ahead and define what mod is. So we say that A and B are equivalents mod n if they both have the same remainder when divided by n. And so we write this as A is equivalent to B mod n. And so what we're really saying is, suppose we know that, okay, when I divide A by m, I get some like xm plus z. And when I divide B by m, I get some like ym plus z. It's okay for y and x to be different, but we have to have the same remainder z. And so as an example, I could say that 9 is equivalent to 5 mod 4, because when I divide 9 by 4, well, that's equal to 2 times 4 plus 1. And when I divide 5 by 4, well, that's equal to 1 times 4 plus 1. And so we share the same remainder. So and I could also say that 9 is equivalent to 5, and that's also equivalent to 1 mod 4. And I could also say, well, if I had 13, well, I could also write that as, I wrote that times 4. It's 3 plus 1, so I'm getting a plus 1 with kind of a lot of things here. And so a lot of things are equal under in mod. And so we might ask, is this an equivalence relation? So as a quick refresher, an equivalence relation has the properties of reflexivity, symmetry, and transitivity. And we can partition the set into different equivalence classes. And so reflexivity, that's saying, okay, so mod is defined on the set of integers. And so let's suppose we have some integer, well, I'll say a equals some z mod n. And so is it the case, or yeah, I guess we're really asking here, is it the case that is a equivalent to a mod n? And so that's your question. And so yeah, well, I guess if we can write some like a is equal to b m plus c. Well, of course, if we write a like that itself, then it will have the same remainder when I divide a by m as when I divide a by m. So yes, it definitely is reflexive. And also symmetric, right? It doesn't matter kind of which order I talk about with my like a and b here. If a is equivalent to b, I can also say that b is equivalent to a mod n, because they both have the same remainder z regardless of which order I write them. And then also if a and b have the same remainder z, and if b and c have the same remainder z, maybe c over m is alpha m plus z, well, they're still going to have the same remainder z. So it would also fulfill transitivity. And so we can see that, yes, this is an equivalence relation. And actually, mod is pretty clear to see what the equivalence classes are, right? So if I have something mod 4, I'm asking, like, what's the remainder when I divide by 4? Well, I have 4 possibilities, right? I could have a remainder of 0. Maybe I divide it perfectly. Or I have a remainder of 1, remainder of 2, or remainder of 3. If I had a remainder of 4, that would go back to 0. If I had a remainder of 5, that would go to 1. And so yeah, so I can have these four, these are the equivalence classes of the mod 4 equivalence relation. And so yeah, so that's kind of what does it mean to take something mod another number, and why is it an equivalence relation? So let's talk about this like kind of mod world, because it might not be intuitive to say that, okay, yeah, I know that 7 is equal to 11, right? Mod, like we're working mod 4, or it's obvious that like 0 is equal to 4. Maybe this is kind of a strange thing to be thinking about. So let's suppose yeah, we're talking about yeah, so I guess kind of a key thing here is if you're talking about addition, you can reduce, and subtraction and multiplication, you can reduce everything mod 4. So say if I had maybe we said, I don't know, 21, or let's say 20 x cubed minus 10 y squared plus 5z, and we're wanting to say, I'm taking this thing mod 4. So one thing to recognize is that, okay, I'm asking what's the remainder of this entire expression when I take it mod 4. So actually I can think about this as individual expressions. I can think about, okay, if I take 20 x cubed mod 4, that will give me some remainder, right? And then I could take negative 10 y squared and get some remainder. And I take this 5z and I get some remainder. So I have like 3 remainders mod 4, and I can then add those remainders up. And then I take that, then I could take this mod 4 again to get something. So I can have view each of these things as maybe this is some element like a, b, and c, and I'm asking, okay, I want to have like a plus b plus c mod 4. Well, if I have a is equal to something mod 4, and I'm able to basically add them together. So here I could say, okay, well, I know that 20 x cubed, well, if I take this mod 4, 20 divided by 4 is 5 with a remainder of 0. So this will be equal to 0, even regardless of what the x cubed is. Doesn't really matter here. And then with the y squared, that will have an impact. But I could say, well, 10 is equivalent to, if I take 10 divided by 4, I get 2 times 4 plus 2. So I could actually write this as negative 2y squared. And then if I take 5 mod 4, I'll get 1. And so then I could, yeah, this is like equivalent. These things are equivalent mod 4. And so kind of you can think about addition, subtraction, multiplication, working, you can reduce every component mod 4 to get something that you then reduce. So yeah, so you have these properties that hold about the Vermonts space, but a subtraction, but division is a bit different. So you might like think about division as, okay, I'm wanting, say I'm talking about, maybe we'll change mods here, and I'm saying maybe I'll take mod 11, and I'm asking, okay, is it the case that instead of division here, we'll actually work with inverses. And so because division doesn't really make sense in the mod space, and so instead of asking, instead of saying, okay, say if I wanted to say, okay, like maybe I'll say, okay, is it the case that 4 over 4 equals 1 mod 11? Well, what we do with division is we multiply these things and ask, okay, does like 4 times this other element like equal 1? And 4 times 4 is at 16. If I take that mod 11, I get 5. And so instead of doing division here, I'm going to have to like ask, okay, what times 4 is equivalent to 1 mod 11? And that's what I'm kind of saying. Instead of division is what I do. I do modular inverses. And so how to find modular inverses? So one method is kind of, we call inspection, or in this case, you kind of see what it is and then you check it and verify it works. So say maybe you think, okay, well, 4 times 3 is equal to 12, and that's equivalent to 1 mod 11. I take 1 times 11 plus 1. And so maybe you can see, okay, then 4 inverse is equal to 3. That might not be so clear initially, and so you also have the option of the extended Euclidean algorithm. And the Euclidean algorithm is a method for finding greatest common denominator, or the GCD. And so say I want to take the GCD of, you have to have so first to have an inverse, you have to have these things be, you have to have them be relatively prime to each other, or co-prime. So I couldn't find the inverse, say, of 11, right? Because if I'm taking 11 times what is equal to 1 mod 11, well, whatever I multiply by, I'm still going to get this to be equal to 0, right? Because I'm multiplying by 11. So I can't have inverses if I'm not, these things are not co-prime. But say for this, they are 11 and 4, so I'll take the GCD of 11 and 4. Well, that's equal to, so to do this with Euclidean, I say, okay, well, 11 equals, I'll divide that by 4, and I get, okay, 11 divided by 4, that's equal to 2 times 4 plus 3. And maybe I'll write this, okay, so I know 3 is equal to 11 minus 2 times 4. And so now I found, okay, I have 3 here and I have 4, and so I'll ask, okay, what's the GCD of 4 and 3? And then I can say, well, 4, that's equal to 1 times 3 plus 1. And then I say, okay, I got 1 equals 4 minus 1 times 3. And so now I've gotten down to 1 here. And so I found, okay, actually, yeah, like I can, the GCD of 4 and 3 is 1. And there, and I've kind of found like the GCD of 11 and so I guess here I'm finding like the GCD of 11 and 4 that's equivalent to the GCD of 4 and 3. And so I found the GCD of 11 and 4 is 3, and that's equivalent to GCD of 4 and 3. GCD of 4 and 3 is 1. And so, okay, I found that, yes, indeed, these are co-prime, which I knew that before. But now we can kind of build up, and we can find what this inverse should be. And so we'll rewrite 1 using what we've kind of gleaned here. So we'll say, okay, 1 is equal to 4 minus 1 times 3. And I actually know what 3 is from my prior equation, so I can say, okay, well, that's equal to 4 minus 1 times 11 minus 2 times 4. And so now I can simplify this. So I get 4 minus 11, and then minus a negative, so I get a positive 2 times 4. And so I can have 4 plus 2 is 3, so I get 3 times 4 minus 11. And we know, okay, this is equal to 1. And yeah, so 1 is equal to 3 times 4 minus 1 times 11. And yeah, so then I can actually say, okay, well, this minus 11 times some number, maybe it isn't 1, but it is in this case. This actually is, if this is equal to 1, then I've actually found something that, okay, I multiply this by 4, and then yeah, so this is like the 4 inverse, and or this would be like 4 is also 3 inverse. But these things together, they multiplied together, they'll be equivalent to 1 when I reduce things mod 11. And so, okay, then I've found the modular inverse of this is 3. And so instead of like trying to ask like what can I like divide here to get something, I'm gonna instead take the inverse. Okay, so we also with mod oftentimes like to reduce things mod a number. So say if I have say I'm asking you to find 7 we'll say, yeah, 7 to the 5th mod 13. So this and we're wanting to like kind of get it into like the most reduced form of something between 0 and 12. And so one approach would be, okay, I'll like multiply this out like so many times, like 7 times 7 times 7 times 7, and reduce that. mod 13. A quicker approach is to use a kind of recursive approach to say, I know that 7 to the 5th variables of exponents that's equal to 7 to the 4th times 7. So if I could find what 7 to the 4th, and 7 to the 4th, that's equal to 7 squared times 7. And so with this approach, it's a lot faster than, say, if I wanted to find 7 to the 17th, I'd have to find, okay, 7 squared, that's equal to 7 to the 4th, and I could square that again. Or I'll say maybe 7 to the 8th times 2, if I'm finding 7 to the 16, and 7 to the 8th is equal to 7 to the 4th times 2, so I get and then 7 to the 4th is equal to 7 squared. So I kind of take one thing, I square it, take that and square it. And so yeah, so basically this will take me it'll take me like log 2 of this time. So I'll take log 2 of 16. That's like 4 times, as opposed to 16 times if I were to kind of do it one by one. So this approach is much quicker, and so we'll do that. So let's okay, we can find 7 squared. That's equal to 49. I take that mod 13. So 13 times 3 is 39. So I can get equal to 10 mod 13. So that's 7 squared. I also could write this kind of computationally as equal to negative 3 mod 13. And that can be helpful to kind of say, okay, 7 squared is equal to negative 3 squared equal to 9 mod 13. I also could definitely say 7 squared equals 10 squared is equal to 100. And then I'll get like 13 times 7, which is 91 plus 9. I take that mod 13, and then this 13 times 7 turns to 0, so then I get 9 mod 13. And so that's 7 to the 4th is 9. And so I take 7 to the 4th times 7. Well, that's 9 times 7 mod 13. And so then I get 63 mod 13. And I know that 13 times 4 is equal to 52. So then I get the whole thing is equal to 11 mod 13. And so I can kind of do this recursive strategy to iterate and find things mod 13, but it'd be a lot trickier to do this if I was saying I have to do something like 7 to the, I don't know, 121 mod 13. So I could do this. I could find, okay, that's I have 7 to the 64 plus 7 to the 32 plus like maybe 7 to the 16, and I can kind of keep going and like find all of these things, but that'll take quite a bit long, quite a while to do that. But we have this approach with Vermonts little theorem, Vermonts little theorem that can help us solve this. So Vermonts little theorem tells us that if we have some A and we have we have prime P, we have A is co-prime to P. So A does not have to be prime itself, but it cannot be be a multiple of P. And so if I take A, raise this to the P, I will get I'll get A mod P, and if I take A to the P minus 1, that's equivalent to 1 mod P. And so here I have a mod 13. So if I and it doesn't really matter what this is as long as this thing is not a multiple of 13. So I could say, okay, well, I know that 7 to the 12, that's equivalent to 1 mod 13. I also know that 6 to the 12 is equivalent to 1 mod 13 because 12 is 13 minus 1. And so I can write 7 to 121 as 7 to the 12 to the 10 times 7 mod 13, and I know that this 7 to the 12 is 1, so I get 1 to the 10th times 7, which is equivalent to 7. Sorry, 1 to the 10th times 7, and that's equivalent to 7 mod 13. So I could do that. I also, say if we were asked 7 to the 125, mod 13, I can write this as 7 to the 120 times 7 to the 5th. We found 7 to the 5th before as being 11, mod 13. And so I could say, okay, well, this is 7 to the 120 that's equal to 7 to the 12th to the 10th, which is equal to 1. So I get 1 times 7 to the 5th, and that's equivalent to 9 mod 13. And so, yeah, so kind of I can use both the Vermonts little theorem and the recursive approach combined, or I can use just one or the other depending on what the problem, what's more helpful for the problem. But both approaches are quite valuable in knowing how to solve mod problems. So hopefully that gives you an idea of what is mod, why do I reduce things mod a number, and how can I work in the mod space. Thanks for watching.